Hi all. This video will be on finishing up our discussion on extreme value theorem and discussing at least two examples related to that. So extreme value theorem, what it states, it's a general metric space fact in this class. If we have a compact subset of a metric space, and we'll see how this assumption of compactness is in general necessary, and if we have a continuous function on that space, then there always exists a minimum and a maximum. And by minimum, we mean that the function value at the minimum is equal to the infimum, and the function value at the maximum is equal to the supremum. And as discussed in the lecture, the infimum is bigger than minus infinity, and the supremum is less than infinity because the function is bounded. We showed in the lecture that any continuous function on 0, 1 was bounded, but the same proof applies to k with exactly the same reasoning as there, except that we would modify the distance slightly that is used there in the space. Okay, now all these proofs of extreme value theorems and similar statements, and also how often you use compactness, and this also relates to one of the homework problems, always follow the same rubric. The idea is that you first find a sequence that approaches what you want or satisfies some of the features that you want, and then you extract a limit of them, and then you hope very dearly that that limit is what you want to find. So we find an optimizing sequence. That means we find an xn such that limit as n goes to infinity, and these xn should be in k, of fxn is equal to the infimum over all the values k. And at this point, I'll say that we will prove only the case of infimum. The supremum is identical, except that you are approaching to the supremum. Now, why is this possible? This is using sup properties. So when I do in the proof, I'll add a little bracket here to explain in more detail some steps that we're using. If we define the set A to be all the values f of x, x and k, and so this is sometimes denoted f of k, then the infimum of x in k of fx, what this really means is that this is the infimum of this real valued, this set of real values. Now this set is closed and bound, well, we don't know if it's closed yet actually. It is bounded. So then the infimum is bigger than minus infinity. And this means that there exists a sequence of points yn in A such that limit as n goes to infinity of yn is equal to the infimum of A. This is true for all sets of real numbers, and this is proven by considering that you can always find an element in the set that is slightly bigger than the infimum. At most 1 plus n bigger than the infimum. This you wouldn't have to justify. This is something you can certainly use in this class. So for every n, you can find just yn, and that sequence then would satisfy that limit of yn is equal to infimum. So we have such a sequence. Now this is an element in A, and what does it mean to be an element in A? Means that for every yn in A, there exists an xn in K such that f of xn is equal to yn. And this leads exactly to this statement, because now f of xn is equal to yn, and we just said that the limit is equal to that. Now, if you would were writing this all of this stuff you do not need to write, but you should be aware that there is an argument like this, and you should know how to do this argument. Because while here, I would allow you to say that by properties of the infimum, there exists such a sequence, you should know why it is true and what it is based on. Okay, so we have a sequence. Now we apply compactness. So since K is compact, and this is one of our assumptions, then there exists a subsequence x and k in K, and there exists an x in K such that limit K goes to infinity, x and K is equal to x. This is what it means to be a convergent subsequence. And sometimes I'll use, say, convergent subsequence in K to emphasize that the limit is actually in K. Now, the limit could be in the bigger space X, but here, for compactness, we're really insisting that the limit lies in the subset K that we are interested in. This is related to the fact that the subset K has to be closed for it to be compact. Okay, so we found this element. These function values are going down. So let's conclude the proof by taking a limit. So since f is continuous, limit as k goes to infinity, fx and k is equal to fx. And let's see what is this limit. This is the same thing. Now this is a limit of real numbers. So this limit is the same thing as the limit of the full sequence f of xn. And this was infimum over all the k's, all the points in k of fx. Now there's a slight abuse of notation here that I'm using x for this fixed value and x for the points in the arbitrary points. So let's fix that by adding a little asterisk here. That way we don't abuse notation in this proof. Okay, so we found our sequence. Now, what this is saying, so if we set x min is equal to x star, we want to show that there exists such an x min, then fx min, well, it has to equal fx star because these are the same, is equal to the infimum over all function values in K. And that is what we wanted to find. And that's what we call, well, that's what we mean when we say that the infimum is attained. So this is often a scheme of the proof of when you want to say something about continuity, a simple scheme. You try to find a sequence of points. You make that sequence converge in the second step, and then you analyze what happens in the limit. So in this case, the function values are getting close to the same. There's a small remark here that in this step, we are using something. If limit as n, so recall that these were called yn earlier in the proof. If limit of yn, and these are real numbers, is equal to, say, something y, then, like you prove in your homework, for any subsequence, the limit of y and k is equal to y still. And what we're using here, we're not using the fact that x and k converges. We're using on the function side that the function values converge. And this holds actually for the full sequence f of xn. So we have two sequences, xn and f of xn. We know that the function values converge, but we don't know that xn converges. And that's something that you have to be careful in this proof. But otherwise, it is a fairly direct error. Now, let's give an example of how this theorem is applied. If you have a function of 3 real variables, so this is a function on R3, that is, say, x1 times x2 3 times x1 times x2 plus x3. This function is continuous, at least very intuitively. There will be a separate video discussing actually how you would prove such things. But this function is continuous. So we want to show that this function attains its maximum on some given set. Here S is the unit sphere. That is all the points in R3 whose norm is equal to 1. So there are 3 things that we need to check. So one thing is that F is continuous. And it is a product and sum of continuous functions. In lecture, we showed this by looking at maps, say projection maps. So one function saying mapping that to x1, and another function mapping that to x2, and another map to x3. So these projection mappings are continuous. Now, okay, so the function is continuous. We are looking at restricting the function S. It's defined on all 3, but its restriction onto S is also continuous. And S is closed. And this we'll see by the easiest way of seeing this is that if we have another function, we define another function, x1, x2, x3 to be x1 squared plus x2 squared plus x3 squared. Then this function is continuous. And the set S is equal to the pre-image of the set 1. This is a closed set, and pre-images under continuous functions are closed, so S is closed. Again, this is something that we will have a separate video on. Okay, so we have a closed set. S is also bounded because S is contained in the unit ball centered at 0 of radius 2. Why is this the case? Well, if X is in S, this means that x1 squared plus x2 squared plus x3 squared is equal to 1. This is the membership condition. Well, this means that distance from x to 0 in the usual metric, if you take the square root of this, is equal to 1. Well, if the distance is equal to 1, then it certainly is less than 2. So x is in B02. So every element in S is also an element in that. Therefore, S is a subset of B02. So we get that because it's in some bounded radius, so there exists an R such that the subset is in an R. In this case, R is equal to 2. So it is a closed and bounded subset by Heine-Borel. S is compact, and therefore by extreme value theorem that we just showed, F S to R has a maximum, has minimum and maximum. And that concludes that example. Another brief example of something where things fail, no maximum, say, is if we maximize x1 squared on the set, and I phrase this really in optimization language now, x is contained in the set S, where S is equal to, say, x1 plus x2 plus x3 less than or equal to 1. Now, S is closed, but not bounded. So not compact. Well, this doesn't mean that there is no maximum. We still need to find to show that that this function attains arbitrarily large values, well, if we look at a sequence of points, so let's set Pn equals n minus n 0, then Pn are all points in S, and let's call this our function f of x, just to make it simpler to refer to it. Now f of Pn is equal to n squared, and limit as n goes to infinity of f of Pn is infinity. So f is unbounded. I mean, this also means that the set, by contrapositive or contradiction, that the set S cannot be bounded itself, because then it would be compact and F would be bounded, but we just saw that this shows that it's unbounded. So there's no maximum.